Alright, so in this video we're going to go over solving an initial value problem using Dirac delta. The first thing we want to do is take the Laplace transform of both sides, as we've been doing pretty often in this chapter. So we have s squared y of s plus 4s, oops, you can't forget about your initial conditions. So we have minus 2s plus 4. Alright, now for the second term you have plus 4sy to the s. And that's going to be minus 8, because 2 times 4 is 8, plus 3y of s. We'll make that a y of s. Now the trick of this problem comes in the very beginning. You need to know how to multiply, or not multiply, find the Laplace transform of a Dirac delta function. Well, we know it's not all that hard. It's just f of a, so in this case a is 3, f of negative 3 times e to the negative 3s. And we could combine them, but it's actually going to be easier here if we don't, so I'm going to leave it like that. First thing you want to do is group the terms with y of s on this side, and then add the terms that don't have over. So we have y of s squared plus 4s and plus 3. And then it's going to be equal to e to the negative 3 times e to the negative 3s. 4 minus 8 is negative 4, so we're going to add that over, so it'll be plus 4 over here. So 4 minus 8, and then plus 2s. Alright, now what you gotta do is to divide this. This actually factors. We're gonna have s plus 3, s plus 1. And that's gonna leave us with y of s is equal to e to the negative 3, e to the negative 3s. Let's keep these separated here. And the reason we keep them separated is because this one has an e to the something term. And that means, or yeah, it means it's going to be a, what's it called, a step function. So we're going to anticipate that here and do these separately. And now what you'll see here is we have two Laplace transforms. Oops, I already wrote y of s. So now what we need to do is find the inverse Laplace transforms of these two functions. Let's start with the non-step function one. So that's this one. Let's do that over here. So we have 4 plus 2s is equal to over s plus 1, s plus 3. And that's equal to a over s plus 1 plus b over s plus 3. Of course, just regular partial fraction procedure. Not too bad. A s plus 3 plus b s plus 1. So let's say s is equal to negative 1. We're going to get 2 is equal to 2a. So a is equal to 1. And b, let's say s is equal to negative 3. Negative 3 plus 1 is negative 2. Or sorry, yeah, negative 2. And negative 6 plus 4 is negative 2. So b is also going to equal 1. So let's erase this and remember that a is equal to 1 and b is equal to 1. So I'm erasing the partial fractions because that's the work we did. So we have a is equal to 1 and b is equal to 1. And now what we're going to write here is the inverse Laplace transform. So I actually erased it, but it doesn't matter because both the coefficients are 1. So what we had was 1 of s plus 3 plus 1 s plus 1. So we get e to the 3, or negative 3t plus e to the negative t. Not too bad. So that is our inverse Laplace transform of the second term. But now we need to do it for the first term. So let's do that here. Let's move that over so we have a little more room. E to the negative 3 is just a coefficient, or a constant. So we're going to leave this e to the negative 3s out and do the partial fraction this way. Because what we're doing is we're realizing the e to the negative 3s means it's a delay. And if there's a delay, we need to do the Laplace transform a little bit differently. If you're struggling with this, you should look at the other video where I do the inverse Laplace transforms of step functions. But to refresh your memory, we just do the partial fraction neglecting the step function, or the step term, which is e to the negative 3s. So you just neglect the e to the negative or positive whatever term. But this is e to the negative 3, and that's just a number. So we leave that over s plus 1 and s plus 3. Now it's just partial fractions. We get e to the negative 3 is equal to a s plus 3 plus b s plus 1. Not too bad. S is equal to negative 3. We get b is equal to e to the negative 3 over 2. Oh, negative. It's going to be a negative. And then a is going to be s is equal to negative 1, so positive 2. A is equal to e to the negative 3 over 2, a positive. I'll do that over here. The inverse partial fraction. E to the negative 3 over 2 is just a constant. And since they're both the same with the exception, I'll write this one a little clearer, that this is a negative. So we can factor out an e to the negative 3 over 2. And then this is going to be e to the negative t. But remember, since this is a step function, we need to include that delay. So we need to do t minus 3. So e to the negative t minus 3. And the t minus 3 is in apostrophes. And then b is negative, so we're going to have minus e. And then here we have negative 3, and in apostrophes t minus 3. And then that whole thing is in apostrophes as well. So now that we have the two inverse Laplace transforms, we actually just combine these together to find the initial value. So I'm going to erase this up here to give us some room to write it. And that should be plenty. So first thing we do is write the regular term, e to the negative 3t plus e to the negative t, and then plus e to the negative 3 over 2 distributed to e to the negative t minus 3, this whole thing's in apostrophes, minus e to the negative 3, and then t minus 3 in apostrophes here. And don't forget, we have to include the delay, so it's just represented by a 2 t minus the delay, which is 3. And again, if you have trouble with the step functions, rewatch the inverse Laplace transform video on step functions. But all in all, not too bad of a problem. And that is how you solve an initial value problem using Dirac delta.